is not Rahul. The topic of discussion today is machine learning. My point today, or my goal today, is not to make you all experts. Or there are very few participants. I can see that very few participants, but my goal is not to make all of you experts in machine learning, because that's not going to be possible, right? It's not possible to make somebody an expert in 1 day or 2 days or something like that. As a matter of fact, you can't become an expert in machine learning even with 2 or 3 years of experience in it. It involves a lot of hard work. It involves a lot of dedication. It involves a lot of programming. It involves a lot of mathematics as well. But what we can do is try and understand what machine learning is, what machine learning can do, and what it cannot do. Right? Most importantly, that is what is important. Most people don't realize what it cannot do. That they started applying machine learning to everything and anything and everything, even though it doesn't really apply to them. So what we'll do is I have a small presentation ready for you, and I'll get that going. I'll fire that up, and we can start our talk with the presentation rather than you having to see my face all the time. You can essentially see the presentation instead. Let me see if I can share my screen. I'll share screen to share. I hope you don't mind me turning off my video, my personal feed, right? Because I would like to lie down as I'm actually recovering from an injury, and I'd like to lie down in between. I don't want you to see me lying down, so I probably turn off my own video feed, right? I'll just keep the presentation running, but there seems to be something wrong. Okay. Okay, I hope the presentation is visible. Can you see the presentation? Is the presentation clear? Can somebody give me a feedback? Is the presentation clear? Are you able to see my screen? Are you able to see my screen? Are you able to hear me?
Yeah, hello.
Can you see my screen?
Yes, everything is very clear. Thank you. It's you're okay, audible fine. And yeah, it's all good.
Yeah. Can you see me right here? Please wait. Can you see me right? Can you
yes.
see the marks?
Fine. Yes.
So that should be fine. Let's get on with our discussion on machine learning. Let's see what it is and what it is not. Right? And like I said, at the end of this webinar or seminar or whatever you want to call it, you will be able to read books on machine learning, and you will be able to talk to people about machine learning. And probably talking to people is the best way to learning something. Right? So you'll be able to do both of these things, but of course you will not be able to create a humanoid robot. You will not be able to create an AI assistant, nor will you be able to win the Alan Turing Prize. But so let's look at what this concept of machines that learn are, right? By definition, the term machine learning kind of implies that it involves machines learning to do things. It involves machine learning to do things, and that means we need to define the term learn itself. Right? Before we talk about machine learning, we might need to define learn itself, the term learn. But then if I go about defining each term, it's going to be a very boring lecture. So let's not do that. Instead, let me tell you straight up front that all programs learn, right? All programs learn. If you define learning as being able to or understanding how to accomplish a task, right? If you define learn as being able to accomplish a task, right? Being able to follow a bunch of steps and then accomplish a task, then of course all programs can learn. For instance, if you have a program that calculates the tax of a person, right? A person's tax returns, then the program is indeed actually learning how to calculate the tax of a person, right? You give him a formula, and the machine essentially now knows how to calculate the tax, right? So in that sense, every program actually does some kind of learning, right? There is some kind of learning involved in every programming task. But then how exactly is machine learning different from these tasks, right? I'll just show you one example here, by the way. I've actually written a JavaScript code here, which is basically a hello world program. I mean, if you know anything about computers, you will know that hello world is probably the first program that you write in computer science when you learn a new language. And this is a hello world program in a language like JavaScript. And what is this computer doing? Hey, computer, please print hello on my computer. Right? That's the task at hand. I'm asking the computer to print hello on the screen. And what is the computer doing? The computer essentially, when it runs this program, it is able to print hello on the screen. Or in other words, you can say that the computer now knows how to, or rather, it has learned how to uh, print hello on the computer screen or on the console. Right? The computer now knows if it uses this code, then it knows how to print hello on the screen. So you could say that the computer has now learned how to print hello on the screen. So even a simple program like this involves some level of learning. But then if you look at it, computer is basically just like a Jagavan. You know what a Jagavan is, right? A Jagavan is basically a warrior who follows instructions from his master. He doesn't do anything on his own. You tell him to go die, he'll die. You tell him to kill someone, he'll kill you. So he's just a person who follows instructions. So computer is also like that. So there's an old joke about how computers are. They say that once a scientist told his computer to go to the market and buy eggs, but the computer never came back after that. Why? Because he did not tell him to come back. He just told him to buy the buy eggs from the market, right? So it bought the eggs and it stayed in the market. It never came back. So that's a joke. It sounds like a joke to me. I hope it was a joke to you also, right? So it's basically only following instructions. Even though it is learning to do things with ordinary programs, it is simply following instructions. It is not really, there is no level of comprehension or any level of intuitiveness associated with it. So, so then how is machine learning different from ordinary programs, right? I'm going to borrow words from Arthur Clarke. I hope you've heard of Arthur Clarke. I'm sorry, Arthur Samuel. I'm sorry, not Arthur Clarke. Arthur Samuel. Arthur Samuel in 1956, he was a pioneer of game intelligence and things like artificial intelligence and all. People like John McCarthy, Arthur Samuel, these are all people who have a place in history, in the history of artificial intelligence. So Arthur Samuel says that machine learning is not a field that basically teaches the computers to learn. It does not simply teach a computer to learn, but it also teaches a computer to learn without being explicitly programmed, right? Without being explicitly programmed. You can see that our Hello World program, will go back 2 steps. Our Hello World program, although it is learning how to print hello, right? We have explicitly asked it to print hello. The computer is not doing it on its own, right? We've explicitly asked it to print hello. And that is how machine learning is different from other programming, other forms of programming, right? Here, we don't explicitly program the computer to do everything it is doing, right? We're only asking it to, or rather we enable it to be able to program, to work in certain ways based on what you call data, right? Using data or examples. We'll see all that later on, right? But then why do we need machine learning? Now, why do we need machine learning when we do have a lot of other algorithms, when we do have a lot of other algorithms that can be used to solve problems? Why exactly do we need machine learning, right? The thing is, when you look at a problem like adding 2 numbers or multiplying 2 numbers or calculating the tax, creating a calculator, all these tasks are pretty deterministic, right? Pretty deterministic in the sense, if you know the inputs, you can predict the output, right? For instance, adding 2 numbers, A and B, if you're adding 2 numbers, if you add 2 and 3, the result is always going to be 5. You can be always sure the result is always going to be 5. It's not going to be something else. Right? So addition is a pretty simple problem, right? Computationally speaking, I told you that my area of Stefan told you that my area of specialization is computational complexity theory. And computational complexity theory is an area that studies what all programs are solvable, how much, what kind of programs are solvable. You can just look at a problem and say whether it is solvable or not. Right? Things like that. That's what we study in computational complexity theory and theoretical computer science. So these are all simple problems when you look at them from a computational complexity standpoint. Right? It's fairly straightforward. You add 2 numbers, you get the result. It's always going to be 5. However, there are problems that are not easily solvable. There are some problems that are not easy to solve. For instance, if I ask you such questions, right? I give you an image of an MRI of a tumor, and I ask you, is this tumor cancerous, right? Or maybe you like listening to, or rather, you're watching YouTube, and then YouTube is trying to figure out whether you would particularly like Yeshudas's song, right? Would you like to listen to Yeshudas's song, right? Or what is the stock price of Flipkart going to be in 2023, right? These are questions that don't really have an X equal to Y answer. We don't have a straightforward answer to this. In 2023, what would be the price of Flipkart stock? We have no idea. Would TKM ICTP be something like a national level company? Would it be a listed company by 2022? We don't know, right? These are questions that don't really have a straightforward answer. And so you cannot create an equation like what you did for addition, or you cannot create a circuit like you did for addition for these kind of problems. And like we saw earlier, computers are generally good at only solving problems that have a definite set of instructions to follow, right? If you can give them a definite set of instructions, then the computer would be able to program it. But then, like I said, these things, you cannot have a definite set of programs, right? You can't just look at an image and then say, yeah, this is 5 centimeters longer. I don't know how big tumors can be. I'm really sorry for my lack of biology knowledge. Assume that you have a 5 centimeter long tumor. I mean, it may not be carcinogenic, right? It may not be, I'm not carcinogenic. What I mean is it may not be malignant, right? It might be a benign tumor, right? So you would never know what it is just by looking at its size or just by looking at its color. It might be a far more complicated task. And so it is not easy for a computer to do it. So, so these are the kinds of tasks that machine learning works with, right? These are the kinds of, I mean, these are some examples of tasks that machine learning would actually be useful in solving, right? Machine learning is definitely not useful at solving A is equal to B. Of course, machine learning can do that, right? Machine learning can be used to add two numbers if you want. If you want, you can teach a machine learning algorithm to add two numbers. It's possible. But why would you do that? That's the question. When you can do it very easily, why would you want to do that? So essentially, these are the kinds of problems that machine learning is looking at, right? So if we are not really programming it explicitly, then how exactly are we telling our machine learning algorithm how to do it? Right? We use examples or data, right? We use our previous examples or data to indeed teach our algorithm how to work, or teach our computer how to solve a problem, right? We use data or our previous experiences, right? Not always previous experiences, as we'll see with reinforcement learning and all that. We'll see that it isn't always previous experiences or something like that. It's basically just data, right? Data could be anything. We'll see what data is later on, right? So we're essentially using data to tell our algorithm how it should work, right? We'll tell our algorithm how it should work using data. If you think about it, this is kind of how we are in real life. Human beings are in real life. For example, how did you learn to shoot a basketball? How did you learn to shoot a basketball? You first shot a ball. Of course, you may have watched Michael Jordan shoot around, and you felt inspired. You watched his videos, and then you understood that to make a shot from 20 feet apart, you need to place your hand in one particular. You need to orient your hands in a particular way, and then shoot it at a particular angle. Right? You've observed Michael Jordan. Right? You've observed Michael Jordan, and then you've learned from him, right? You observed the way he makes his shots, which means the angle that he applies to each shot, the power that he applies to each shot, the place that he's shooting from, right? All these things, there are many things that you can observe about Michael Jordan, right? And then based on these, you're saying, yeah, if I shoot at an angle of 45 degree with a power of, let's say, 45 watts, let's say that's a lot, but we shoot with 45 watts of power, and then at a distance of 25 centimeters from the court, then it is definitely going in, right? It's going in. However, if I shoot at an angle of 46 with a power of 45 at a place 25 centimeters from the shot, then it is not going in, right? So based on such observations that you make, you're essentially concluding that your shot is going in or your shot is not going in, and then you decide how to shoot. Right? That is one possible way you can approach this problem. Another possible way you can approach this problem is essentially by just going to a basketball court, right? Just going to a basketball court and then shooting the ball in the basket yourself, right? You're going to try to shoot this basketball without observing anybody, without doing anything. You're just going to shoot the ball. Now, if it goes in, yeah, that's good, right? And now I know that there is something that this was indeed a good shot, right? Or if it doesn't go in, yeah, it's a bad shot. So I should probably make adjustments to my shot. So you can teach yourself, or you can observe somebody else doing it. Either way, you're essentially using your experience or your data, right? The data that you have. And using this data, what you do is you essentially create a model, right? You create a model for shooting basketball, right? Creating a model on how to shoot a basketball, right? This is one particular term that not many people quite understand, right? It's a term that not many people even understand. They go about using the term a lot, but they don't really know what it means, right? So a model in science or in computer science and mathematics, model in general means it's a representation, right? It's basically a representation of some kind of a real life system, usually in the form of an equation, right? Usually in the form of an equation, right? You're trying to represent a real world event or a real world experience or something, right? A real world occurrence in the form of a mathematical equation, right? In the form of a mathematical equation, most often a mathematical equation, right? You may have other kinds of models as well, but mathematical equations is probably the most powerful way of representing your equation. So you could say that the equation on how to shoot a basketball could look something like this, right? Angle, right? Let's say angle x into angle plus, no, let's say a into angle plus b into power minus c into place or distance, whatever you call it, right? This would give you a value. And if this value is greater than 25, let's say the shot is going to go in, right? The shot in. If this value is less than 25, the shot won't go in, right? So this is one possible, I'm just writing shot out, right? This could be one possible model on how to shoot a basketball, right? So you're essentially creating models for your data, right? You're essentially creating equations to represent your data, and you're going to help the computer, or rather the computer is going to use data. The computer is going to use data to figure out such equations, right? This is what machine learning is. If you want to stop and go away right now, you can go away, because this is what machine learning is, right? The machine learning, the algorithm is essentially going to try and figure out such equations, right? It's going to figure out such equations, and then if you give it future values, right? If you give it values, unknown values for these three values, it will tell you whether the shot is indeed going to go in or not, right? That's what machine learning algorithms do. So let's look at one such problem, right? You have self-driven cars these days. If there are any spelling mistakes here and there, please ignore them, because uh, I did not go through I did not scrutinize my PPT. So I'm sorry if there are any spelling mistakes or wrong headings or something like that. So please ignore them and assume that they're all correct. Usually what I tell my students is teachers are always correct. So if there is a spelling mistake, then by heart that as the spelling. Right? From now on, that will be the spelling of that word. Right? Anyway, you have a car here. A car has come to a junction, and then the car does not know in which direction it should go. Right? This is one possible situation for machine learning can be applied. Right? Should I go to the right? Should I go to the left? Right? This can, based on its experience, probably based on, maybe this is the shortest route, but this is the least what do you say, traffic jammy route, I don't know, but yeah, busiest. This is probably a far more busy route, right? This is a busier route, but this is probably the longer route, right? So the computer has to decide which direction it should go in. So such tasks can be solved using machine learning. Now let's take a look at one particular example, right? This was one example that we took up earlier. What is the stock price of Flipkart going to be in 2023? Now, you know that the stock price is dependent on a lot of things, right? The stock price can depend on the oil price. It's surprisingly, it can depend on the oil price, right? Because if when the oil price is high, it affects the gold price, it affects this, it affects the business, and then people start investing, people do all that. Yeah, my economics is bad, but my common sense tells me it should depend on oil price, right? Similarly, it should also depend on the price of dollar, right? If the price of dollar is higher, then you want to invest in dollar, not in Indian rupee, things like that. Right? Also the year, maybe there is something special about the year. For example, in leap years, Flipkart tends to do well. During other years, Flipkart doesn't do well. Things like that, right? Again, the price of gold could determine it. The stock price of Walmart could determine the stock price of Flipkart, right? Because Walmart owns Flipkart these days, and so it could depend on the stock price of Flipkart. So you could say that it could depend on a lot of things. But for example's sake, what I'm going to assume is the stock price of Flipkart is somehow dependent only on the year, right? I'm just assuming, right? I'm just assuming the stock price of Flipkart is dependent only on the year. And magically, all these other things are determined by the year, right? Assume. This is not true. This is definitely not true. But I'm just assuming for experience, for simplicity's sake. And what I'm going to do is I'm going to plot the stock prices of Flipkart in the previous years. For example, in 2009, the stock price of Flipkart was 20 rupees. And in 2011, it rose to 40. and then it rose to 70, it rose to 90, it rose to 120, it rose to 130, and all this. But if you observe this data, if you carefully observe this data, you'll be able to see that. By the way, I've just done, in case you're wondering what happened now, I've just divided these y coordinates by 10 and written them as 2, 4, 6, and like that, right? Rather than writing 20, 40. Similarly, I've just written the years as 2, as 1, and maintained the gap between them, right? The gap here is 2, the gap here is 3. Similarly, the gap here is 2, the gap here is 3, like that, right? So I've basically just scaled it down to a more, to a simpler values, right? But still, the trend is still going to be the same, right? This trend of data is still going to remain the same. So don't worry about the coordinates. Just look at the trend of the data. You can see that it is indeed forming a line, right? All of the, or rather the way in which Flipkart's stock price behaves with respect to the year, right? With respect to the year is linear, right? Linear. It looks like a line, right? Anything that looks like a line is called linear in mathematics, right? So it looks linear, which means maybe if I can draw a line through this, just like I've drawn now, maybe in the year 2000, no, maybe in the year, not 2013. What was the year? I forgot the year. 2021, isn't it? In the year 2021, if I draw a line from here, right? If I find out the y coordinate corresponding to that, then I'd probably able to predict the value of Flipkart, right? The value of this is probably 14, and I don't know, right? So this is kind of how machine learning works. So you're trying to find out a curve that passes through all of the data points or the data experiences that you have, right? You're trying to figure out a curve that basically fits through your data, right? And the curve obviously has an equation, right? Most curves have easily creatable equations, right? They have equations that can easily be created. Most curves, but not all curves. It's not easy to create an equation for a curve all the time, right? Sometimes it can be very difficult. But let's assume that this is the trend that Flipkart is following, right? So you could say that Flipkart's stock price can be determined using this particular equation, right? It can be determined using this equation. And so for every year, right, for a particular year, you can see that for y equal to x equals 2, y would have a certain value. For x equals 3, 5, all these values, y would have a certain value. But the issue is, in real life, data doesn't always look linear, right? You can't always draw a line through the data points, right? Maybe the stock price is varying in a very not so simple way. I don't know what word to use. It's probably varying in a very strange way that is not easy to understand, right? It's following a very unpredictable trend, right? But at the same time, the general trend is that it is rising, right? You can see that the general trend is rising. So what do we do when we can't really get the actual uh, uh, trend of data? What do you do when you can't really get the actual trend of data? What do you do in machine learning when you can't really have an actual trend of data? It's simple. You create an approximate model, right? You create an approximate model. I mean, this is Paul Walker, if you know him. I actually knew who he was after his death, by the way. Paul Walker is an actor, is a Hollywood actor, who is famous for his role in this movie franchise called Fast and the Furious. I don't really watch movies, but I've read that he was a very popular Hollywood superstar. So he was famous in this series called Fast and Furious series. And in between the shooting of one of those movies, he actually passed away in a car accident, right? It was not really on the set of the movie, but he passed away. But the issue was they actually did not want, I mean, Paul had actually left a lot of his, well, actually not completed a lot of his shoots, right? All of those, there were a lot of scenes in which he was actually involved, which they had actually not shot by them. Right? So they had no other option but to use a dupe, right? So what they did was they got in touch with Paul's brother. I don't know his name again. You can look it up if you want. Right? They got in touch with Paul's brothers. Actually, they contacted Paul's brothers, both of his brothers, and you can see that they're actually quite similar, right? You'd actually, if you did not know who Paul Walker was, and if I asked you which of these is a Hollywood star, I think both of them look pretty good, and they are both qualified to be Hollywood stars, isn't it? They both look pretty good. So you can say that. So what they did was they used the approximate solution they had. They did not have the actual model. So what they did was they started using the approximate model, and they completed the whole movie using Paul's brothers. Not just him. There's one more brother. So they used Paul's brothers to actually complete the shoot. They applied CGI and all that, and made him look exactly like Paul Walker, right? So what do we do when we don't have an actual solution? When we can't really find an actual solution, or when we can't really create an actual model? What we do is we come up with an approximate solution. So your approximate solution can be anything, right? How do you tell a computer what the approximate solution is? That is the whole, or rather, how do you help a computer come up with an approximate solution? That's the whole task behind machine learning, right? So this, as you can see, this is actually an approximate solution, but it's actually a very bad approximate solution, because you can see that the data is lying here, but the approximate solution that we came up with is here. So another possible approximate solution could look something like this, right? This is pretty good, right? It's pretty good because it's very close to one of those points, but it's not really passing through all these points, right? This is also an approximate solution because you can see that it is also passing through one of the points and it's very close to all these points. But of course, this is definitely a better solution, right? It's a far better solution. And this seems like an even better solution, right? Because it's passing through so many of these points, and the other points are quite close to it. Apart from this point, right? Apart from this point, which is quite far away, almost every other point is pretty close to it, right? So this could be an approximate solution. And what you just saw is actually a very powerful machine learning technique, a regression technique known as linear regression, right? It's a very simple, but at the same time, a very powerful regression technique, a machine learning technique, or a statistical technique known as linear regression, right? So machine learning is essentially the process of fitting your curve onto the data points you have. You have an area called curve fitting in mathematics. You have areas called statistics in mathematics. So it's basically an application of these two areas, right? It's an application of curve fitting. It's an application of linear regression. It's an application of differential calculus. It's an application of linear algebra, right? It's basically an application of a lot of mathematical techniques so that you can come up with a good curve that can model the data that you have, right? So let's take a look at, let's take an abstract view of how machine learning is different from other programming languages, right? I'm sorry, how it's different from other kinds of programming, right? A normal program, if you look at a normal program, you give it a program, right? You give the program into the computer, right? With normal programming, you give the program into the computer, you give the input, right? You give the input, and then the computer gives you the output, right? You give the program, you give the computer the software, you give it inputs, the computer will give you the output, right? Machine learning is slightly different. In machine learning, you give the computer data, right? And then you give it maybe experiences, right? The corresponding outputs that you expect, right? You give it the data and also the outputs that you expect for this data, right? By data, it could probably be previous experiences or something like that, right? Essentially giving it data and then experiences, right? Or the results of these data, right? What would happen to this data if you actually gave it to an actual program, right? If there was an actual program to solve this problem, what would be the result for this data, right? That is what this is, right? That's what this is. So you take such experiences that you have from real life experiences that you have, and you feed in the data, and you give in the corresponding results for those data, and the computer is essentially giving you a program, right? It's essentially giving you a program as a result of it. And then you can use this program to calculate the results for unknown values, right? You can use this program to calculate the results for unknown values, right? For example, with our Flipkart example, we were giving it data, right? The data means the years, isn't it? The years 2009, 2010, we gave it 2009, 2010, all those years, and the corresponding stock prices, right? We gave it the corresponding stock prices, and then the computer will essentially create a program, or rather, it's not a program, it will basically create a model. It'll create a model for us, and then we can use this model or this program to predict values for unknown values, right? The output for unknown values, for example, 2023, 2050, right? The computer would be able to tell us these answers. So this is what, this is how a machine learning program is different from other ordinary kinds of programs. Okay, so there are basically three kinds of machine learning algorithms, right? Some say that there are four, there are five, but let's just keep it simple, right? There are things called semi-supervised, all those things. We won't talk about all that, but we'll just talk about the most commonly used or the simplest three types of machine learning, or the simplest three classifications of machine learning problems, right? The simplest three kinds of machine learning problems, right? There are other classifications. There things like semi-supervised are there. Like I said, we won't talk about all that now, right? We'll only talk about these simple three classifications. And the first one is what you call a classification task, right? What you call a classification task or a supervised learning task, right? You have something called a supervised learning task, right? A supervised learning task is much like the example that we saw earlier, where we were watching Michael Jordan shoot the ball, and then we were learning how to shoot the ball, right? We were observing somebody, right? We had data, right? We essentially had data, and we had labels, right? We had angle data, we had data for angle, we had data for power, we had data for distance, right? And then based on this, we also had the result, right? So just like that, you have a data and then you have a label. And the label means the output corresponding to the data. So let's take a look at this particular example here, right? Let's consider a task where you're trying to figure out if a photo that you have in front of you is indeed a photo of Michael Jackson or not, right? Another MJ. We were talking about Michael Jordan, who was MJ. Now we're talking about Michael Jackson, who is another MJ, right? So this is definitely Michael Jackson, right? This is also definitely Michael Jackson. We know this. We know this. So what we do is we feed these things into the computer. We feed these images into the computer, both positive examples and negative examples, right? Positive means yes, negative means no. Right? We give them both positive and negative examples, and somehow magically, right? Some magic happens inside the computer, right? That magic is basically machine learning. It happens inside the computer, and then it creates a model, like we said earlier. It creates a model, and then using this model, you'll be able to predict if indeed Salim Kumar's photo from the movie Charika Dajandu is indeed a photo of Michael Jackson or not, right? So this is what you call supervised learning, where you have data, where you feed in data and also the label corresponding to the data, right? You give him an image and you also tell him whether this image is indeed a positive example or a negative example or something like that, right? So if you can somehow extract features like the amount of makeup that is applied, the skin color, maybe you would be able to come up with a graph that looks like this, right? Maybe these yellow dots are indeed Michael Jackson images, right? Which means a skin color that has a value of a certain value, let's say 244 or something like that. The skin color is 244. The average skin color is 244. And then you have something called the amount of makeup you're probably able to tell from the picture. Assume you're able to extract these features, right? Assume you're able to extract the amount of makeup that is applied on Michael Jackson's face or the person in the picture's face, right? If you're able to do that, and if you're able to maybe plot it like this, right? And maybe you'd end up getting a graph that looks like this. And you can see that these are all Michael Jackson images, right? This because we know this. We're telling the system that these are all Michael Jackson images, right? And these are all not Michael Jackson images. These are not Michael Jackson. The purple ones are not Michael Jackson images, and the yellow ones are indeed Michael Jackson images. Now, based on this input, what the computer will try to do, or the machine learning algorithm, what it will try to do is it'll probably try to come up with some sort of a model, right? It'll try to come up with some sort of an equation, right? This equation could be that of a circle that looks like that, right? It could be an equation of a circle that looks like this, or it could be a circle that looks like this, right? So based on the predicted model, you can see that these green dots, which are actually unknown points, and we don't know if it's Michael Jackson or if it's somebody else, right? These are new data points that are coming in. So we don't know if they are indeed Michael Jackson images or somebody else's images. So what we have is, if you're predicting with this model, you can see that this particular example is not Michael Jackson. But with this one, it will be Michael Jackson. So based on the model that our machine learning algorithm comes up, the result will vary, right? The result will vary. So with this particular model, you can see that this guy would be classified as Michael Jackson. This person will be classified as Michael Jackson, but this person will not be classified as Michael Jackson. This person, this would have basically classify none of these green points as Michael Jackson. As a matter of fact, actually, this is a much better classification, right? Because these are quite close. You can see that these are quite close, and there's a high probability that these are indeed Michael Jackson photos. So this is basically a much better classification than this one, right? We won't talk about such intricate details of machine learning algorithms, about optimization, nothing like that we'll do. But I'm just showing you that multiple possible models are possible for the same data, right? The same data can give you different results, right? The same data can give you different results based on the machine learning algorithm that you're using, right? So this was now imagine, right? Now imagine a different. Now this is another example. Now imagine you have a slightly different kind of classification where we're able to classify data points using a line, right? Earlier we saw how we can classify it using a circle, but assuming that we now have points that can actually be classified into two classes using a line. Now assume it's not just one line, you have three classes here, right? You have three classes, assume you have three classes, and you can use lines to separate them. You have four classes, right? you're finding out there are indeed 4 classes. There are 5 classes. Now what if uh, each point, right? Each point on this graph essentially ends up being a class of its own, right? Earlier we were talking about 1 class, and when we saw 2 classes, 3 classes, 4 classes, 5 classes. Now assume that there are infinite number of classes, right? There are infinite number of classes, or in other words, every point on this graph essentially forms a class of its own, right? Or in other words, every point is behaving like a class, right? So each prediction that you make is basically going to be a class. So such a kind of classification task is what you call a regression task, right? A regression task is one where you have infinitely many classes, right? You have an infinitely many classes, or basically you're trying to predict a continuous value, right? A continuous value. Mathematically speaking, you're trying to predict a continuous value. Earlier with classification, right? Earlier with the previous examples of classification, you could see that our class we had only 4 discrete values here. It could either be class 1, it could either be class 2, it could either be class 3, it could either be class 4, it could either be class 5, right? These are 5 classes. Now I'm talking about a situation where you have infinite number of classes, right? And a task where you have infinite number of classes is what you call a regression task, right? So, so basically, since it's defined for every point on this curve, you can say that it is a continuous task, right? So one example of a regression task is the linear regression that we saw earlier, where we were actually drawing a continuous line, isn't it? We did not have a broken line. We did not have broken line. So we were basically predicting points that were on the line, right? With classification, what were we doing? We were drawing a curve that could basically separate data points. And with regression, we are basically drawing curves that can predict future values, right? We're predicting, we're using curves to predict future values on that graph itself, right? Both are prediction only. So this is an example of a regression task, right? We basically, the stock price of Flipkart is basically a continuous value. It's a continuous value. It is defined at every point, isn't it? It's defined for 2:51 p.m. today. It's defined for 2:52 p.m. today. It's defined for every moment. The stock price is indeed defined for every moment. It's not like it's defined for 12 o'clock. It's not like it's defined for 13 o'clock or something, 13 o'clock, 13 hours, something like that, right? It's defined everywhere. So the goal of classification, or the goal of supervised learning, right? The goal of supervised learning, we saw that supervised learning includes both regression and also classification, right? It involves both regression and classification. And supervised learning, the goal of supervised learning is to find an approximate function, right? The goal is to find an approximate function that maps data to the label, right? To find an approximate function that basically maps the data to the labels. Now, the next kind of task is called the clustering task. It's called the clustering task. Here it's slightly different, right? It's slightly different here. Here we don't know what we're looking for, right? We don't know what exactly we are looking for. We're just given a set of data. We're given data. We're just given data. We don't have labels here. Right? We don't have labels here. We are given data, right? And we're asked to find if there are indeed some structures in this data, right? For example, if you look at this particular task, I'm assuming that this is basically the average frequency and average amplitude of a song that you're playing, right? A song that, or maybe you're asked to listen to 10 or 20 songs, right? You're asked to listen to 10 or 20 songs, and then you make a plot of the average frequency and the average amplitude in that particular song, right? You're basically plotting each song as a data point based on the average frequency and average amplitude. So this would be song 1, this would be song 2, this could be song 3, this could be song 3, 4, like that. Right? Each of these points is basically a song. And now my question is, are all these songs sung by the same singer, right? Are there songs among these songs that were indeed sung by the same singer, right? You listen to 20 songs or 30 songs. Now my question is, I'm asking you, are there songs in this cluster, or rather in this group of songs, that were indeed sung by the same singer, right? So if you look at this graph, you can see that there are indeed some points that are appearing close to each other, right? So when, logically speaking, or rather intuitively speaking, when certain points lie close to each other, you can say that there is probably some kind of relation between them, right? And that relation between them could be that it was indeed sung by the same singer, right? That relation could be that they were all sung by the same singer, right? But we don't know if if they are sticking together because they were sung by the same singer. We don't know if they are indeed sticking together because they were sung by the same singer. We don't know why they are sticking together, but we can observe that they are indeed sticking together, right? We can observe that these songs are indeed sticking together. We don't know why they're sticking together, right? But they are sticking together. So you're assuming, right? One assumption is that they could be sticking together because they were all sung by the same singer, and that is why they have the same average frequency, similar average frequencies, and similar average amplitudes. That could be one reason why they are. But then it could also be because these songs are from the same genre, right? They could be from the same genre, and maybe that is why they are sticking together. But what my point here is, we don't know why they're sticking together, but we know that there are some points that are sticking together. The goal of this particular task, right? The goal of unsupervised learning here is, right? The goal of unsupervised learning here is to find structures, right? To find structures in data, right? You're basically given data, you just given data points, you're not given any clue about it, right? You're going to plot this. Because this is a 2D space, this seems like a fairly simple task, right? Since we are talking about just two values here, right? We're talking about data points with just 2 dimensions. We have just 2 dimensions here, and because you can plot it on a 2D space, it is fairly simple for any person to look at this and say, yeah, there is one group here, there is another group here, there is another group here, there's another group here. But think of it in maybe 4 dimensions, right? What if there are 4 dimensions, right? Even 3 dimensions you can imagine, right? Beyond that, it's slightly difficult to imagine, right? Beyond 3 dimensions, it's actually quite difficult to imagine. And so you cannot really just draw it and then draw circles around it and say, yeah, these are all groups. So that is where, when you have more than 3 or 4 dimensions, when you're plotting these points in more than 2 dimensions, you cannot easily find such structures, right? And which is where you use computer, which is why you use computers. Computers don't need to imagine, right? They don't need to imagine. They just use their memories to manipulate data. So anyway, the goal of unsupervised learning, right? The goal of unsupervised learning, or you could also say the goal of clustering, right? The goal of clustering is basically to find such group of points that are sticking together, right? Trying to see if there are indeed relationship between points, right? If there are points that are related to each other. For example, you can say that these points are related to each other, but we don't know how they are related. Right? We don't know how they are related, but for the moment, let's assume they are related because they were all sung by the same singer, right? And because there are indeed four groups here, you can say that there are 4 singers, right? You can say that 4 singers, or maybe there are 4 genres, right? There are maybe 4 genres, right? Maybe 4 singers or 4 genres, but the point is there are 4 kinds of songs here, right? So that is what we're trying to find out. What are the clusters that are there in our data, right? So this could be one possible cluster. This could also be a cluster, right? So again, depending on the algorithm that you're using, the machine learning technique that you're using, you'll get different kinds of clusters, right? So like I said, the goal is to find underlying structures, right? Now we're going to talk about a very, very, very interesting class of machine learning algorithms, which a lot of people use. I mean, a lot of people talk about, right? They talk about as if it is the future. They talk about as if they know it really well, but in reality, most people don't know it well. Not even I know. I mean, I'm not a big expert in this area either, but it is something that has attracted a lot of attention these days, right? It first came, or rather, it first attracted a lot of attention in 2011-12 period, when Google actually used it to defeat the human champion of this game called Go, right? There's a Southeast Asian game called Go. I think it's a Thai game. I'm not sure. There's a game called Go. Google actually created a small, not a small, it was actually a pretty big program. They created a program which was able to defeat the world champion of Go, right? The program they created was called AlphaGo, right? So it was in 2011 or 12, I don't remember the year exactly. Maybe I'm wrong about the year. So anyway, what they did was they created this particular program, which was actually able to defeat the world champion in Go, right? And it was called AlphaGo. And the algorithm that they used, or the concept that they used behind the scenes, was this concept called reinforcement learning, right? It's another class of learning algorithms, reinforcement learning, right? Simply put, it is much like a pet owner training its dog, right? It's simply like a dog owner training his dog, right? It's much like a dog owner training his dog. And why do I say this? Because you know that this is particularly difficult. I forgot the name, but whatever it is, just listen. Right? Why does a dog roll over, or why does you teach your dog to roll over, and then when the dog actually rolls over, you actually feed him something, right? And what does the dog understand when you do that, right? From the dog's perspective, it understands that if I roll over, when I hear roll over and I perform this action, right? When I hear roll over and I perform the action, I will actually get rewarded, right? So the next time you say roll over, the dog is going to do it, right? Because it wants that reward, right? It wants that reward, and that's why it's actually doing it. So this class of algorithms that actually work like somewhat like this, where you basically let the computer do things on its own, right? You tell the computer a list of things it can do, right? You don't explicitly give it data to learn. You don't use any kind of supervised or structured anything, nothing of that sort. You don't really give it any kind of previous past experiences at all. Rather, you're going to ask the computer to create its own experience, right? For example, I've actually created a small simulation which I think would make more sense than me trying to tell you what it is, right? Assume that we have a problem where a computer is actually trying to defeat a human opponent in uh, in a game of football, right? The computer wants to defeat a human being in a game of football, right? We have these computer games and all these things where computers essentially uh, try to defeat human beings, right? So imagine that we are trying to create a software. We're trying to create a software where a computer is essentially going to try and beat us in a game of football. So I will just place that screen here, right? So I've just created a small simulation. I hope it is visible. Can you see the football field and the football and a lot of red and blue dots? Is that visible? Are you able to see the screen, the football?
Yes, I can see red and blue dots.
Can you see the green field and football
Yes,
line?
yes.
Okay, fine. So I think you can see that you can see the simulation, right? So assume that our goal here, right? Our goal here is to make sure that the blue team hits a goal, right? Our goal here is to make sure that the blue team hits a goal. So the computer can what it can do is it can just pass around. It can do different tasks, right? We can give it a set of actions that it can perform, right? And the actions it can perform are it can hit the ball, right? It can hit the ball anywhere. It can either hit it to the blue balls, it can hit it to the goal, it can hit it outside, right? It can hit it to its teammates, it can pass it to and maybe a red team also, right? Which would be a bad pass, of course. A blue team passing to the red team would be a bad pass. So although it is a bad result, we would want to let the computer do that so that it can simulate a real life example, isn't it? Because it's a game and we want it to be slightly realistic as well. So what the computer would do is it would basically try out all possible things it can do, right? Possible things it can do, and then it will figure out the best possible way of indeed hitting a goal, right? We've said that you will get rewarded if you hit a goal, and then the computer, what does it do? It keeps on trying to do things till it actually goes into a goal. So if I just try to execute this, you can see that the first, if the ball goes straight to a red team, right? It's a bad decision, and you're basically losing the ball, right? When you've lost the ball, you won't get a reward, right? However, uh, let's try another set of moves. Let's try another set of moves. You can see that now it's passing the ball to blue teams, right? It's passing the ball to its own teammates. These are all good moves. Obviously, these are good moves, isn't it? These are good moves, but it's basically passing the ball to its own teammates, right? These are good moves. But the best move is not passing around. The best move would be one where he hits a goal, right? So the thing here is the computer is essentially trying to come up with the best course of action, right? It's not just trying to uh, uh, accomplish that task that it is supposed to do, but it's going to figure out the best course of action also. So you basically give it a list of actions that it can perform, right? You basically give it a list of actions you can perform, and then you're going to let the computer figure out what is the best way in which you can achieve rewards, right? So what we'll do, we'll come back to this particular the simulation in a moment. I'll show you how exactly reinforcement learning works, and then we'll come back to this, right? So basically, assume that this robot is your program, right? This is your program. So you tell this program what all this program can do, right? And then there is an environment, right? There's an environment on which it is actually performing these actions, right? For example, if you're stranded on an island and you have no idea what to do to survive, what do? You try out different things, isn't it? You take a stick, you try to create fire, and then the environment responds back to you. If your fire making technique is right, then what do you get? You get fire, isn't it? So you get rewarded with that fire. So your the environment will basically let you know the state it is in, right? When you've made a fire, you're essentially in a successful state, right? When you're in a successful state, you get rewarded. So based on this rewarded, you will decide what the next action should be, right? So the issue here is, when do we actually reward this particular person? For example, in our island example, do we actually reward this person when this person finds 2 dry pieces of sticks, or do we reward him only when he's actually able to create the fire, right? If we reward him only when he's actually making the fire, then the person will have no idea what course of action it should follow to actually create that fire, right? He'll probably sit there, he'll take sand, and then he'll keep rubbing sand on itself, and he'll keep on doing that, but no fire is being created, right? He'll not be able to create fire, but he'll keep doing that, expecting some reward will come, right? This is because we are delaying the reward, right? This is because we are delaying the reward. However, if we don't delay the reward, there's a high probability that we'll keep on making the same mistake. For example, he found a stick, right? I'll reward him, right? The moment he finds a stick, I'll reward him. Fine. Now he's taken a stick. But rather than rubbing these sticks to each other, he's going to keep on hitting his head with that stick, right? Okay, I will not reward him for hitting his head, but still I've already rewarded him for taking the stick. So he's taken a stick, so he'll try out different things he can do with that stick. And finally, maybe when he'll create fire, you can reward him again. But then he has wasted a lot of time in between the hitting on the head and actually creating fire, right? He's done a lot of unnecessary actions in between. So the place where you actually reward this person actually matters a lot. And we can see this using a football example once again. You can see that they're still passing around because it is still not made a goal, isn't it? You can see why is it keeping on passing, right? Because I told that if you pass to your blue teammate, it's a good move, right? If you pass to your blue teammate, it's a good move. So the computer is actually keeping on doing it because it is getting rewarded, and it is keeping on passing to its teammates. But what is the actual reward? What is the actual goal of this problem? It is to hit a goal, right? The computer is not doing that because we've already given it, we've already rewarded it, right? By the way, these simulations are not accurate, or nor these examples are accurate. These are just simple examples for people to understand, right? Don't take these examples too seriously. Now, similarly, now assume there's another situation. The computer actually hit a goal in his first move, which is a good thing. Now assume that there's another set of moves where you can see that the ball is being passed around, and you can see that you've actually passed it to a red team. Now you've passed it to a red team, and the ball has gone to a blue team also, right? And a red team actually hit a goal for my team, right? The red team actually hit a self goal for my team. Please keep this point in mind. The red team actually hit an own goal for my team, right? They hit a own goal for my team. What is the issue here, right? The assumption with the computer, if I reward my computer for an own goal, right? If I reward my blue team for an own goal that the red team actually did, what happens? The computer will now try to pass the ball more to the red team, right? The blue team will now start passing the ball to the red team, assuming that the red team would hit own goals all the time, right? But it won't, right? The red team might accidentally hit an own goal. Once in a while, it might hit an own goal like we saw now. But the possibility of that happening is actually very low, right? In reality, the possibility of the red team actually hitting an own goal is actually quite low. So you should not always reward the blue team for passing the ball to the red team, right? Or for a mistake that it made and somehow the ball reached the red team, you should not reward it. So it matters where you actually reward or rather the whole problem, or the biggest problem in reinforcement learning is figuring out when you should reward or what actions are to be rewarded, at what point should you reward. So basically it's going to be a very, very complicated task, right? It's quite a complicated task. It might seem like the computer is actually just simply taking actions and it is rewarding itself and all that, right? And simply learning by itself, right? It's not a simple task. It's actually a far, far more complicated task than what you think. And also the number of simulations, or the number of times the computer has actually to do this exercise, right? The number of times the computer needs to do this exercise that you see here, right? The number of goals it has to actually hit, or the number of goals it has to miss, ultimately decides this number of times it has to play this game is actually going to be quite high, right? It's going to have to run the simulation many million times or many thousand times to actually be good at doing this. And so it was actually going to take a long time, or you would require something like a supercomputer to simulate it, right? So it may not be possible to do reinforcement learning effectively and quickly on an ordinary home PC or something like that, right? So it takes a lot of time to do it. That's one of the biggest problems that reinforcement learning has. It's quite a complicated task. The algorithms are not simple. It's quite difficult to optimize, and also deciding upon when do you reward, what kind of rewards do you provide, not what kinds of rewards, but what actions are to be rewarded. All these things are quite complicated, right? So that is reinforcement learning, right? So those are the three kinds of or the primary classifications of machine learning tasks, right? You're essentially trying to maximize the reward by choosing the best action, right? That is what reinforcement learning is doing, right? It is maximizing the reward by choosing the best action, right? Now, we've been talking about training machine learning models, or rather teaching machine learning models to do things, right? We've been talking about all this all for so long. Now let's talk about training in more detail, right? Or rather, I'll probably skip this, right? I think you have a pretty good understanding of it already. We'll just skip that, and we'll go and talk about data itself, right? We'll talk about data itself. You can see that there is a saying that in machine learning and in data science, data is basically king, right? Data is the king in machine learning and data science, or even in statistics, right? In mathematics and statistics, data is basically king. So, by that, what I mean is, it all depends on how you use data, what kind of data you choose, the way data is selected, the way features are extracted. All these things determine the effectiveness of our machine learning algorithm, right? You might be wondering why I've put this particular image here, right? There is this concept called the survivorship effect, which is popular through which became popular through one story during the World War, right? I'll probably try and tell you the story as quickly as possible. During the World War, there was this group that was constituted in the United States, which was called the Statistical Research Group, and it was headed by, or rather, it involved a lot of. It was a group that included a lot of brilliant mathematicians and brilliant statisticians from around the world. Right? One of the goals that they had was to figure out what kind of armoring, or where they should apply armor to the aircraft, right? To what kind of armors, or the exact positioning of the armors on these fighter jets, to ensure that these fighter jets indeed came back safe, right? They noticed that most of the fighter jets that came back alive, they had received their shots on their wings and on their tails, right? And the engines, surprisingly, you can see that the engines indeed were actually not harmed at all, right? And they concluded that we should probably start applying armor to the portions that you can see, right? To the main body, and probably the edges of the wings and the tail end and all these parts. These parts require special armoring, because those are the areas where these people are shooting the most, right? That's what they concluded, right? They concluded that, yeah, these are the areas that these people are shooting at the most, right? They're shooting here, they're shooting in these areas. And that is why, and so we should probably apply armor to these areas. Please bear in mind that if you apply armor to the whole plane, the plane is actually going to become too heavy, and then it's going to be difficult to, it's likely going to consume a lot of fuel. You don't want the plane to consume a lot of fuel. You want it to be able to fly faster. So you would want to reduce the amount of armor, but at the same time, you would want to make sure that the plane safe also, right? It stays safe also. So they looked at it and they saw that, yeah, the front portion is safe. The engines are pretty safe. They're not shooting there. These are the portions that they're shooting, and we should probably apply armor to these places, right? surprisingly, there was one of these statisticians in between in this group who said that who actually refuted to this idea, right? His name was Abraham Wald, right? You may have heard of him, right? He's a pretty famous statistician, right? There are people who disregard him also, but he's a pretty famous statistician who's no more. Abraham Wald looked at this image and said, "What are we doing? Aren't we being stupid? Do you not realize that all those aeroplanes that were indeed shot on the engines have not even returned, right? They've all crashed and they've not even returned. The ones that we are looking at are the aeroplanes that have actually come back from war, right? These aeroplanes have actually survived the war. Even though they were shot here, they have actually survived the war. All those planes that were shot on the engine, that were shot on the body, all the other parts, right? They've actually not come back, which means these are not the areas that we should be shielding. These are the areas that we should be shielding, right? Because the airplanes that were shot on the engine have not even come back, right? We're being completely silly by applying armors here, right? So this was the conclusion that Abraham Wald actually came up with, and it was actually correct, right? So my point here is, it all depends on the goal of, or rather the result of everything that we do in machine learning depends on how you manage your data, right? It depends on how you choose your data, the kind of algorithms that you choose, all that, right? So if you choose the wrong data, if you choose the wrong kind of model, then you end up having strange classifications. Like we saw earlier, you can see that these points are indeed very close to the Michael Jackson images, right? These are very close to Michael Jackson images that we saw earlier. But sadly, because of the machine learning model that we applied, these points are actually being classified as not Michael Jackson images, right? So it all depends on how you choose your data, how you model your data, right? So we're also going to talk about this concept of neural networks now, right? This is probably going to be one of the last topics that we're going to talk about, and we will end our discussion on machine learning with deep neural networks and neural networks, right? So you cannot discuss about neural networks without actually talking about these three people, right? For some of you, these faces may be familiar. It's basically Bengio and Hinton and Likud, right? These are three famous scientists. They're all ACM Turing Award winners from 2018, I think, 2018 or 19 or 16, I don't remember. In the past 5 years, they received one of those past 5 years, they received the Alan Turing Award from ACM. And they received the award for their contributions to neural networks, right? Why are they so important? It's because a lot of people think that neural networks is actually a very new concept. A lot of people think that neural networks is something that came up in 2010 or 2020 or something like that. I'm sorry, 2015 or something like that. But in reality, neural networks is very old. It started during the age of when theoretical computer science was actually taking state, right? It came up during the 1945 period, right? The ideas of neural networks are actually formulated during this period. But everybody thought that neural networks were a waste of time, that we would never be able to indeed use neural networks, primarily because we did not have that kind of computational power during those days, right? The computational power that we actually had during those days were indeed quite limited, and so we couldn't apply neural networks. Also, the amount of data that we were generating, or the amount of data that was available during those days, was not enough for neural networks to be effectively used, right? So what exactly are neural networks? You will hear a lot. You basically looking at a situation where you don't know, right? You don't know what those x and y coordinates are, right? Earlier we said this is the x coordinate, this is the y coordinate, and you plot the data, right? Basically, you're given some kind of an image or something like that. Assume that you're given some kind of an image, but you have no idea how to extract features out of this image, or assume that you don't know what exactly these features are, right? What exactly these dimensions are. For instance, if you look at our, please give me a second. I have to forward my PPT to a couple of slides to show you our old example, right? We have our Michael Jackson example, right? So we have the image with us, but we don't know how to indeed extract the amount of makeup or the skin color, right? We don't know how to extract the makeup or the skin color out of this image. So what we do is we basically consider that every pixel, right? Every pixel that is there on this image is indeed a feature, right? I'm going to assume that every pixel that is there on this image is a feature that can indeed determine whether this picture is that of Michael Jackson or not, right? And what do? I'll basically feed this into a neural network, right? I'll feed each of these pixels into a neural network, and this neural network will basically, it's a very magical kind of thing, right? It involves a lot of mathematics, which is why I'm basically skimming over it. This is one area that I extensively use in my research, right? Especially in my research on human-computer interaction, especially with gestures and all that, right? I work on gestures, gesture-based devices and all that, right? That's my primary interest. And also, like I told you, computational complexity is also an area of interest. But I use deep learning and neural networks extensively when I do projects on gestures, right? So this, out of all those machine learning algorithms, this is probably one thing that I use the most, right? Deep learning is probably one thing, and neural networks is something that I use the most. So, like I was saying, you take every pixel and you assume that each pixel is indeed forming a dimension, right? Each pixel is forming a dimension. So you basically have a lot of such. Please give me a second. This thing is causing a little bit of trouble for me, right? Uh, each pixel will now form a dimension, right? A dimension like this. So you'll have so many dimensions, and depending on each of these features, your neural networks is basically going to make a prediction, right? Your neural networks is basically going to make a prediction comparing all these small pixels, right? The pixel values of each of these images, right? So what is this neural network, right? I'm not going to go into the mathematics of it. I will not go into the mathematics of neural networks because it will take a long time to see it. But simply, I'm going to give you a simplistic view of it, right? Like I told you, uh, like each pixel is going to be a feature, right? Now assume that you have a picture with 3 pixels. Of course, you don't have pictures with 3 pixels, but assume that you have a picture with 3 pixels. What you do is you feed each of these features, right? You give each of these pixels into, or rather you take a weighted sum, right? By weighted sum, what I mean is you give a weight, you multiply a weight to feature 1, you add it, weight 2, feature 2, weight 3, feature 3, right? You get a sum, you get some kind of a value here. And then you pass this sum value into something called a non-linear function, right? You give it into a non-linear function. A non-linear function means a function that does not draw a line, right? It does not draw a line, it draws some other kind of curve. Maybe something that looks like this, or maybe there's something that looks like this, or maybe a curve that looks like this. It basically draws some other kind of curve, maybe even a circle, right? It's some kind of, it's some other curve. But usually with neural networks, what we do is we choose one of these non-linear functions. The non-linear functions that we choose usually outputs a number between 0 and 1, right? It usually outputs a number between 0 and 1. And those are the kinds of non-linear functions that we choose in neural networks, right? We call these functions activation functions, by the way. We call them activation functions primarily because of the similarity, or rather we've actually based this concept of neural networks on human neurons. I'm not going to make that comparison because everybody makes it. If you want to compare it to an actual human neuron, simply go on YouTube and probably type, and you'll find 100 explanations on how it is actually compared to a neuron. So I won't do that, right? So in a neural network, what we have is we don't this particular thing that you see in front of you is what is an artificial neuron, right? It's an artificial neuron. And when we combine multiple neurons, right, we get a neural network. So you basically take your features, right? You take your features and you feed it to each of these neurons. You feed it to each of these neurons, and then you connect. You have layers of neurons. This is the first layer, right? And this would be the second layer of neurons. And you feed these neurons, and it finally gives some output, right? We know I'm not going to go into the specifics. It's absolutely fine if we did not understand anything here, right? Because it's quite a complicated topic, and I don't want to give you any wrong impressions, right? If I give you a wrong impression up front, then you might actually understand it. You might not be able to correct the mistake that you learned first, right? So I'm not going to go into the details of neural networks now. I'm just showing you that this is something. This is probably how it works, right? And there are very complicated neural networks. So you'll have very complicated neural networks that look like this, that can apply filters called convolution layers to extract features, right? Basically, what neural networks are good at is they're good at extracting features without us telling what features are, right? With our Michael Jackson image, we did not know what features indeed decide whether an image is Michael Jackson or not, right? We did not know what are those features that indeed decide whether that image is of Michael Jackson. So what we do is we let the neural network decide it by itself, right? We let it pass through different layers, and then the neural network basically decides it on its own. And so I'm not going to, like I said, I won't be talking about neural networks in depth. But one thing I will do is I will tell you the difference between machine learning and artificial intelligence. Right. I think it's best understood in the words uh, of one of the professors from University of Toronto. Right. I forgot his name, by the way. I'm very sorry, I've forgotten his name. Right. Artificial intelligence is basically about making computers behave in ways that make you feel like you're actually interacting with a human being. Right. The goal of artificial intelligence is to give you an illusion as if you're indeed interacting with an actual human being. Right. That's the whole goal of artificial intelligence. Right. It gives you an impression as if you're actually talking to a human being. You might be talking to a machine, but you're not even able to tell apart whether it's a human being or a machine. Right. You have this concept called Turing test. Right. You have this concept of Turing test or the imitation game. Right. You have such concepts that were put forth by Alan Turing. Right. You have which basically he used to explain what AI meant to him. Right. What artificial intelligence meant to him. So it encompasses all technologies that help you achieve this. Right? It encompasses all technologies. So it probably involves robotics. It involves hardware and software. Right? It involves hardware and software. It involves robotics. Right? It involves autonomous cars. It involves all those things. Right? It involves many things that give you an illusion that you are indeed interacting with an intelligent being. Right? It gives you an illusion that as if you're interacting with a human being. Right? The study where where you try to create technologies that give you an illusion that you're talking to an intelligent being. But machine learning, on the other hand, like we saw earlier, it's about automatically improving, right? It's about automatically improving yourself at doing a task, right? It's about automatically improving yourself at doing a task with the experience, right? You're basically given experiences. You get better at doing that task each time you do it, right? You get better at doing it that task each time you do it. So that is what machine learning is. So it's not, the goals of AI and machine learning are completely different, right? There are overlaps. Of course, there are overlaps, but they're not the same, as you can see. And it's about getting better at doing a particular task, right? Machine learning is about getting better at doing a task, while AI is about giving you an illusion of intelligence, right? Now, what about data science? Right? Data science is slightly different. Right? Data science is not artificial intelligence. It's not machine learning. It's actually a technology, right? That basically looks at data of different kinds. It basically looks at data of binary data. It looks at all kinds of data, and then it probably takes in this data and gives you out useful information. Right? It basically extracts useful information uh, data. Right? It takes in data and then it gives you useful information out of it, right? So that is what data science is. So data science is not machine learning. Please don't get confused between a data science and machine learning. They're completely different areas. And this is how I'd probably, if I were to draw a Venn diagram of artificial intelligence, machine learning, and data science, this is probably how I draw it, right? Data science includes some techniques, or rather, it will use concepts from machine learning. It will use concepts from artificial intelligence, but then it also involves areas that are not really part of machine learning or artificial intelligence. For example, managing databases, all these things can actually be part of data science, right? Uh, but there are many deterministic algorithms which are not really part of machine learning. You might use many deterministic algorithms in data science which are not even part of machine learning and or even artificial intelligence in data science. So data science, so you can visualize it like this, right? But machine learning, right? Machine learning, although its goals are different, machine learning is actually an area that comes under artificial intelligence, because machine learning is basically a lot of techniques that help you accomplish artificial intelligence, right? And then there are other areas including robotics, right? There are other areas including robotics that are there in artificial intelligence which are not part of machine learning. But then there are people who say that machine learning has some areas which are actually outside the purview of artificial intelligence. I'm not sure why they say that. They're probably correct. I don't know, but I've never really felt that it is so. I've always felt that artificial intelligence indeed uh, uh, fully encompasses machine learning, right? Now, why has machine learning come up these days? The primary reason why machine learning has become so popular these days is because of data, right? There is so much data that is generated these days, and that has helped us use data to create machines, right? And also the next thing is because of the rise in computational power. We have so much computational power now. And also we have parallel computing platforms like CUDA, right? You have parallel computing platforms like CUDA from NVIDIA, and also many other parallel computing platforms, which have actually made computation available to ordinary people, right? I can perform more computation now on my cell phone than somebody could do in a supercomputer maybe 40 or 50 years back, right? So uh, maybe even on a calculator, even a handheld calculator would have so much power now. So computational power is available these days, and also there are software packages like CUDA and with hardware support from NVIDIA and things like that, which have actually made this computational power available to ordinary people, right? When computational power becomes available to ordinary people, they start doing research on their own. They can finally work on their curiosities, and based on that, they can essentially uh, use these advanced techniques. Now, also other packages like TensorFlow, things like RapidMiner, software tools like RapidMiner have all contributed to the rise in machine learning. Right? These are all software tools that have made access to machine learning very, very easy. Right? These are all tools that have made access to machine learning very easy because they are basically very simple tools, very intuitive tools which don't even require coding. Right? For example, RapidMiner doesn't even require any kind of coding, does not require any programming knowledge to do machine learning with, right? So that is what has made machine learning so popular these days. Also, right, this particular language called Python, which most of you might be familiar with, is also has also played a role in the popularity of machine learning. Obviously, there is always an attraction towards machines that can learn by themselves, right? We're always attracted to machines that can learn by themselves. But then, what if you're not able to program it because the programming language that is used for machine learning was very difficult? Assume, right? What if the programming language that people use was very difficult? Uh, then of course a lot of people wouldn't really do machine learning. They wouldn't want to do machine learning if it was actually a very difficult thing to do. So what Python has done for us is Python has actually made machine learning simple, because Python itself is a very simple programming language, right? This is an internet meme that I found a couple of days back, right? um, uh, when you tell people that you're a data scientist, people think that this is what society thinks. People think that you're actually making self-driven cars. Your friends think that you're working in some lab. Your parents think you're working with some supercomputer. Your coworkers think you're writing some formula. Uh, you think you're doing some magical things, but what are you actually doing? You're just basically importing Python packages and working with it, right? So that is what data science has become today. It is not a very complicated task. It's a fairly simple task, and it's something that anybody can do. And why has Python become so popular, or why has Python become the go-to language for machine learning? You see, most people who work on machine learning are mathematicians, right? Most people who began working with machine were mathematicians. And the thing about mathematicians is they wouldn't want to use a language that is as complicated as C, right? You have a language like C, which just to print hello world, you need to type so much, right? You need to type so much just to print a hello world, right? On a programming language, C++, you'd have to probably type this much. A language like Java, you probably have to type this much. But with Python, surprisingly, all you need to do is type this much, right? That's all it requires for your first program. If you want to print hello world, this is all that is required, right? So this is the primary reason why Python has become so popular. And because it was initially adopted, right? Because it was initially adopted by mathematicians, what happened was mathematicians actually built a machine learning community with Python, right? They built a machine learning community with Python, and almost every famous package in Python was actually created first for Python. I'm sorry, every machine learning package was actually created for Python initially. It was only later on that people started using other programming languages for it. Of course, languages like Java were also used, but most good packages or most easy to use packages for machine learning were actually written in Python or written for Python. Even TensorFlow, right, which is a very powerful neural networks or a parallel computing network that system library that can actually be used for neural networks. It was initially written for Python, right? Now it is available for languages like JavaScript and all, but it was initially written for Python. Right? So it has a really, the fact that mathematicians initially took up Python helped it build a huge community. Right? There was a huge community that was using Python and good at machine learning. Right? Also, one of the reasons that Python is quite popular is because of its package management tool. Package management tools, the way it handles third-party packages, right? For machine learning, you cannot simply write if and for statements and expect to do it easily. Of course, at the core, you're basically using if and for and all that, but you require advanced packages, right? Which makes things easier for you, right? Uh, so since you require third-party packages to do machine learning, you would basically require a convenient package manager also, and Python actually provides it, right? It's very easy to install third-party packages using PIP and all that, right? And initially, Python is very easy to learn. Initially, right? Python is a very easy to learn easy to learn language initially, right? But Python is also a terrible language, right? I say this as somebody who's deeply interested in the performance of a program, as somebody who enjoys fast programs, right? As somebody who enjoys fast programming or quickly programs and execute quickly. Python is also a terrible programming, right? Programming language, because it is an extremely poor performing language, right? It takes quite a lot of time to execute code, right? It has features like vectorization, which can speed up matrix operations and things like that, right? It does support parallelization and all that, threading and all that is supported. But then, no matter what it does, it can never match the performance of a programming language like C or C++ or even modern programming languages like Rust, right? Not even Java, right? It can't even match a programming language like Java, which actually shares a lot of design philosophies with Python, right? Java and Python, they share a lot of design philosophies, but still Java is a much faster programming language. But Java is obviously a much more difficult language to learn for beginners, but Python is fairly simple, like I said, right? So this ease of learning is one of the primary reasons why we use Python. Other than that, Python, I honestly don't. I've never felt that Python has too many other features which make it very attractive, right? It's very easy to learn. It has a very convenient package manager. It has a very strong community, right? That's probably the most important reason, right? That's probably the most recent important reason why people use it now, right? Earlier they used it because it was easy to learn. Now they use it because there's a huge community around it, right? Uh, Now, features like vectorization, yeah, it is there, but yeah, there are programming languages that can do it even better than Python. So that is not a big excuse to use Python, but this definitely is, right? So that is about machine learning. That's about Python. That was a small introduction to machine learning. I hope it made sense to some of you. I'm sure neural networks made absolutely no sense to you, but other than that, I hope the rest of it made some sense to you. And if you have any doubts, you can of course uh, ask me now probably, but I'm assuming that since there are very few participants, I'm assuming that there wouldn't be too many questions. But if you do have any questions, you can ask me.